Okay, what I was saying is what we will do is I will stop, let's say after 30 minutes or so, once I've gone through uh, a major topic, then we can have a question answering session. So if people have questions, what I would recommend you is that just write them down. Okay, so whenever you have a question, just write them down on a sheet of paper. Huh? And whenever I stop and ask for question, prompt you for questions, ask me then. Does that does make sense? So that there is a gap. I mean, there is a balance between the flow of the class and also I mean, I do encourage a lot of questions. I mean, I'm happy that you people are asking good questions, but let us uh, not have multiple quote unquote interruptions so that the flow is there. Huh? Was one thing, and there was a couple of other questions on. And some of you were asking whether this course is going to be fully quote unquote mathematical, or will there be some practical considerations issues that would be considered. Uh, I mean, see, the way I would answer that is that there is no practice without theory, without math. I mean, having said that, once we complete the mathematical nuances and other details, you would definitely go to the practical implementations, because all your assignments will be coding assignments. So they'll all be practice-based assignments only. Okay, and also in the class and tutorials, whenever needed, we will also talk of the practical implementations and the other things. Okay. Okay. That's about it, I suppose. Anything else that any logistics, other issues that we want to discuss before we start the class?
Like we would like to share with you.
Hello, am I
Yeah,
audible?
yes. Yeah.
Yeah, anything you did you have a comment?
Yeah. Are you able to hear me?
Yes, yes, I can hear you. Go on.
Yes, just one suggestion if possible. Uh,
Hmm.
you cover theory and then you give a problem example, right?
For theory and then I give what?
Problems. You explain a problem and give a solution to it, right?
Problem, I didn't follow your question.
Example. Like you
Huh.
will cover a topic, theory of
Hmm.
it, and then
Hmm.
you give example for that, right?
See, these are
A
not
problem.
like these topics are not like your let's say class 12 maths, where okay you learn how to differentiate functions, and then there are some example problems on differentiate functions. It's not that. See, now we are looking at adversarial optimizations or GANs, right? So by practice, what I mean is, for instance, in today's class. I will tell you how to train again practically, right? How does all the theory that we are looking at translate into practical implementation, right? So there are no numerics per se, because it's, as I said, no, it's not like a fundamental calculus or probability theory kind of course where you introduce a concept and there are many, many problems to be solved. It is not that way, right? By practical stuff, I mean the implementation stuff, right? How would you take these ideas and implement those in practice? Does it make sense?
Yeah, that's right. Yeah.
Okay. Okay. Anything else?
Yeah, one more doubt I have. This is about conjugate of a convex function.
Yes.
If we draw a graph of the conjugate of a function, convex function, how will it look like? Will it be inverse of it or
It'll look something like an index.
okay?
Yeah. Okay. Uh, should we continue with the class?
Yes, sir.
Yeah. Let me join through my iPad. Yeah. Also tell me whether this black background and white font is okay with you, or should we have to switch it to white background and black writing?
This is fine, sir.
This is fine. Okay. Okay.
Sir, if possible, just change the color of pen whenever there is a highlighted topic, like note
To
or anything.
that I'm doing, right? I'm looking doing that highlight thing.
No. I mean, when you are taking some new topic, something new, then just change the color so that we can mark it properly, if possible. Otherwise, also
uh,
fine.
but yeah, see, everything that I write is important that way. Yeah. So anyway, so I'll take that into consideration. And also there was some discussions on KL divergence and all that in the group. No, I will like I thought once we cover these topics, it will be clear. Or I'll respond to that. Okay. Okay. So let's start. So just quick recap before we go to the topic of today's lecture. So we were looking at adversarial optimization, right? Or generative models via adversarial optimization. So what is the context? The context is that we want to build a generative model, which is that it takes an arbitrary random variable as input, in this case, a Gaussian random variable, and it generates or it samples from an underlying unknown distribution, right? So we represented that function as g theta of z, where z is an arbitrary random variable, and x cap, just highlight it. So this Apple Pencil is always with my laptop. Whenever I want to write it, it has 0% charge. I don't know why. Anyway, so there's this function g theta that would map an arbitrary random variable z to another random variable x cap. Okay. Now, what do we need? We need a situation where this x cap has a distribution that follows the distribution of data. Okay, which we have called px. Why is that? If this p theta becomes close to px, then we have achieved what we want, because then if you take an arbitrary random variable z and pass it through this function g theta, then you get samples from px, which is the underlying distribution. Okay. Now the question was, how do you set the parameters of this neural network g theta such that p theta, which is the distribution of the output of the neural network, is close to px, which is the which is the input unknown distribution. The solution for that is that what you do is estimate a distributional divergence measure between px and p theta. That will become a function of theta, and set the parameters of this neural network theta such that this is minimized. So if you do this, then the resulting neural network g theta neural network that you get will be such that it will take an arbitrary random variable c as input, and it will output x cap, whose distribution happens to be following px. Now, if you recall the tutorial, how do we solve this optimization problem of minimizing some sort of a divergence measure or a loss function with respect to neural network? All of you know how to do that, correct? Now, this theta star equal to argmin d theta px and p theta. This optimization problem is solved using backpropagation. Is that okay? Any questions on problem setting, the how the problem is set up? So you
Just one
have
query, sir.
hmm,
This X hat is the complete image, right?
X hat as the complete image.
Yeah, and it doesn't depend upon the random inputs we are giving.
It very much depends on the random input, right? Because it is G theta of Z. Z is the input.
Yeah, but it depends on theta parameters, right?
It also depends on parameters, and it also depends on theta. See,
No,
look at the
not theta.
setting.
Okay, when I say input, it's Z, which is a uniform, sorry, normal distribution on this diagram.
It depends on Z, it depends on theta, both of it.
But G is the random, right?
Z is random, correct?
Yeah, then it should not matter what we give, right? It's random, right?
Oh, that way you're saying. Okay,
Yeah.
so what when you said that it does not depend, I thought what X cap that you get does not matter what Z that you get. That's not what it is. So for a given Z, you will get a given X cap. But yeah, but you can choose any input distribution on the arbitrary random variable. Yeah, that is correct.
So whatever we give as Z, because it is random, we'll get the X cap, right?
Post training. Post training. If you train it such that this divergence is minimized, then it is true. You will get an X cap from the distribution. Different Z will give you different X caps. So you remember I told you to look at that this person does not exist.com last time, right?
Yeah,
So
right.
every time you get a different, you give a different Z as an input, you get a different image generated. Okay. But you have to, like, you should not change the distribution of Z. For instance, suppose while training, you have sampled Z from uniform random variable. You should not start sampling from normal random variable when you are doing inference or generation. That is not what should do. What you should do.
Okay.
Okay.
So yeah, does it mean that if X hat is a human face, different Z will give different human faces?
Correct. Correct. Post training, different Z's will give you different human faces. Correct.
Okay. Thanks.
Okay. Right. So now, any other question on this?
So one quick question.
Hmm.
The output is gonna be human faces and human faces only. Matlab mixtures of human faces, or it can be like you can have human faces with different features, let's say 3 eyes or 4 eyes.
Okay. That depends on how good your training has been. That can happen. See, how does that translate to mathematically? Is that if you have made this divergence metric between px and p theta really low, then you will only get images from human faces because px, the data that you have been given, only have like images from the distribution of human faces. That's why you should train it well. See, if you have not trained it well in such a way that this divergence measure has not gone to arbitrary low values, then you will have all these kinds of artifacts. So you will see that in your assignment. So in your assignment, I will actually ask you to train these neural networks. If you have not trained them well, then the output will not be good.
Got it.
Okay. Another question, Bharadwaj.
Hello, sir. Good morning. Just something I was wondering, sir. I was looking at the talk as well that the Afghan authors gave on YouTube. Sir, it was not very clear to me. Like, did they think of this adversarial approach first and then justified it or proved it with maths, or the maths led to the discovery? Like, what came first, like the intuitive understanding or the mathematical foundation behind it?
Okay. Yeah, so that's a general question. See, I've been in this business of research for a decade now. I can tell you for sure that all of my papers or the work that I have done, it's always that we do some empirical experiment based on some hunch. It works, and whenever it works, we backfit the math. Because my firm belief is that if there is something that is working, then there should always be good math behind it or good systematic understanding behind it. But the way this is how I do it, I don't know how others do it. In fact, chronologically speaking, no, as our home minister said, no, to chronology ko samjho. So if you look at the if you look at the chronology, GAN paper came in 2014, okay, which only has empirical experiments. Okay, but this FGAN, which is a much more uh, foundational understanding of what was happening, came 2 years afterwards. So that way, empirical stuff came first, and then math came later. But uh, I mean, this is how uh, things happen, right? Mostly in engineering research. However, while you understand, so to me, always principled understanding is something that I would like. Right. I mean, if you just tell me, give me an algorithm and say that, oh, there is a discriminator, there is a generator, okay, there is these two networks competing with each other, etc. I will not be convinced because I don't know why it is working, what is actually happening, and so on. So that is why when I teach, I always teach math first, from a math first approach, because that is more grounded and principled. Now, once I put down that mathematical foundation, I would connect it to the empirical stuff, which I will do in this today's class. Okay, yeah, but I mean, long, to long story short, in engineering, mostly the empirical science precedes math, but there have been a lot of cases where you come up with mathematical ideas and then translate it to empirical stuff as well. Both happens. Okay.
Got it, sir. Thank you.
Okay. So now the thing is given data and samples from p theta. So now again, okay. So now what is the core question here? That you again, I'm emphasizing this multiple times because it has to just go into your mind. So basically, the question that we have is we have this setup and we want to minimize this distributional divergence measure between px and p theta. Okay. Now, what do we have? What we have at our hand are samples from px, which we call as data. Okay, that is what data is. And we also have samples from p theta. What are samples from p theta? They are simply the outputs of neural networks. How do we get multiple samples from p theta? As somebody was saying, you sample or you get multiple samples from the Gaussian random variable. How do you get the samples from Gaussian random variable? You have this randn function, right? In all pseudo random number generators, right? You get the random numbers generated from random function and give it as an input to g theta. Okay, that is how you get multiple samples from p theta. So now you have samples from d, you have samples from p theta. The question now is how do you compute the distributional divergence d theta so that we can use that as a loss function and back propagate through this neural network to minimize that. That is what we need to do, right? If we take if we take p theta and px and compute the distributional divergence and minimize the distributional divergence and train the neural network using that, this neural network g theta will start generating samples from px. That is the idea, correct? Yeah. So what is the big deal about it is that remember that the biggest problem in all of generative modeling or all of machine learning is that you do not know the distributions, okay, between which you are computing the divergence. You only have samples from it. So you don't know what the form of px and p theta is, but you only have samples from px and p theta. Okay, yeah, that I have written that already, right? So how do we have samples from px? It is the given data. How do we have samples from p theta? It is simply choose different z's and pass them through g theta of c. That would give you samples of p theta. Now, having samples of px and p theta, how do you compute the distributional divergence is the question. Okay. Okay. Now, before going to compute the distributional divergence, I defined a large family of divergence metrics, which we called as the F divergence, uh, of which the KL divergence is also a member. Okay, KL divergence, the forward KL, reverse KL, Jensen channel divergence, all of them are members of this family. We defined F divergence as this particular integral, and this F is a convex function. Okay, so you plug in a convex function, you get a different divergence metric. Okay, that is what we saw. Okay. Now, coming back to our goal was to compute the F divergence between Px and P theta using their samples without knowing the underlying distributions. Okay, so we saw that there is a way to do it. the way to do it is that if you have an integral, okay, with respect to a density function to be computed, you can approximate that using what is called as sample means. Okay. Now this result, which we called as law of large numbers, this one, simply say that integrals can be computed without, okay, or rather with only the samples. Correct. So that is law of large numbers. If you simply have samples from distribution, and if you're looking at integrals of functions with respect to density functions, without having, so please look at this equation. This is pretty important. So this one, okay. So this is actually one of the key equations that we will be using multiple times in this course. That if you want to compute an integral of a function h of x with respect to some density function p of x, I mean, it is also called the expectation of h of x with respect to p of x. You simply take the sample averages of the h of x computed at all xi's, where xi's are coming from px. So in this case, it is data, right? You can compute these sorts of integrals using sample estimates. This is a known result. Okay. Now, how do we use that? If the divergence metric that we are trying to minimize, if we can express if we can express that in terms of expectations over px and p theta, then this divergence metric can be computed using sample estimates from px and p theta via law of large numbers, right? Because we know that we can compute expectations using samples with this result called law of large numbers. Then if we can represent our df in somehow via expectations over px and p theta, then we can compute the f divergence simply using the samples, correct? So now with that goal, we now wanted to express df in terms of expectations over px and p theta. Okay. Now, with this goal, we saw that we cannot represent this f divergence exactly using the exactly via expectations over these two. But what we can do is we can express the lower bounds on df in terms of expectations. Now, instead of minimizing the f divergence, we minimize the lower bound on it. That is the idea. One can ask, no, okay, well, and we set our goal as finding out the g theta such that the f divergence, sorry, f divergence is minimized. Now, instead of minimizing f divergence, you are minimizing a lower bound on it. I mean, is it correct? No, that's not exactly correct, because if you can minimize the divergence itself, then it is great. But the problem is f divergence cannot be minimized exactly without having the distributions px and p theta. Now, because we don't have distributions px and p theta, but only have samples from it, what we do is we instead solve an approximate problem, which is minimizing the lower bound on f divergence. Okay. Right. So now what we should do is, in an issue, we should bound f divergence and express in terms of expectations over px and p theta. For that, we did some algebra. We took the convex conjugate of the f function in the f divergence, and we did some manipulations. And finally, what happened is that we got this result where we expressed f theta, okay, df, the f divergence, as I mean, we carved a lower bound on the f divergence via this expectation. So what is this? There is the lower bound that we obtain will become a function of this another class of functions called tx, right? Now what we are saying is that there is some terminology here which is expectation of some function of some other function f star of tx as x cap is coming from p theta, right? So we know how to compute both of these expectations. Why? I mean, if we know what T function is, then this expectation can be computed using law of large numbers, right? Where you can approximate this using sample averages. I will write down all that and show you how to do it in practice. Okay, so now basically what we did was, yeah, we have expressed the lower bound on the F divergence in terms of expectations over unknown distributions. Now the lower bound that we computed on F divergence, okay, is itself involves an optimization, that itself involves an optimization problem over a class of functions Tx. Now what I mean to say is that if you give one particular Tx, you will get one lower bound on F divergence. And that is something that you should note. Maybe I'll put that as a note here. Okay, this red is too much red. This was okay. Now lower bound on F divergence involves solving an optimization problem over some function classes denoted by T of x. Okay, yeah, this is the moral of the story. See that? Okay, is that now we constructed the lower bound on the F divergence or the loss function that you would want to minimize, and we express that in terms of expectations over Px and expectations over P theta. And the lower bound itself contains an optimization problem that is to be solved over another set of functions, class of functions that we denoted as Tx. Okay, so let me stop here for a couple of minutes and ask questions. Please ensure that all of you are totally with me on this, okay? Because whatever I do now will be building upon this. So ensure that you understand this perfectly, and then we will move on. We'll spend some 5 minutes on this. And this is actually a key equation for GANs. So once we do this, then actually it's all done. Okay. There are a few questions. Aditya.
Sir, I think there's a typo on the line just before this. If you could scroll just a little higher. Um, yeah, the close bracket I think should come just before dx in that line. F star of dx and then the close bracket, because p theta of x should be multiplied with f star of, right?
Oh, yeah. Yeah. Correct. Thank you for noticing that.
Yes, sir.
So this here. Oh, what is this? Some fancy thing. Okay. We have ah, and this is for school goers and kids. Okay, they have made some. Okay, thanks. Lokesh.
Sir, can you please explain how this greater than sign came once again?
Oh,
Like DTF is greater than.
I see. That's the content of last class. But anyway, so if you, yeah, you have to trace back the entire derivation. Um,
No,
did
just
you
the last step.
where
Just
where
the
where
last step.
where
After TX, after T star of
see
X is
you
equal to.
understood why there is this why instead of having small t why capital T came, right? Because you are solving an optimization problem internally, correct?
Yeah, yeah.
Now
I got that. Yeah.
if I pull that maximization out, okay. So this capital T or rather this Tx that we have, right, should be such that it will give you the solution for that optimization problem, internal optimization problem at all x, correct?
Yeah.
Now, suppose there is some tx, with capital T of x, which is a function that would not give you the solution for optimization problem for all x.
Okay.
In that case, what happens? This entire integral that we compute, right, or the maximum value that we compute under that tx will not be, will always be less than the case where you would have gotten the maximum at all x, isn't it?
Okay.
You get it? See, I mean, instead of t star of x, which would give you the maximum value at all t, if you had another function t that would not give you maximum at all points. If it does not give you maximum at all points, what does that mean? It is always less than the maximum, right? It can at
Yeah,
most
yeah.
is equal to the maximum or it is less than the maximum.
Yeah. Okay, sir. Yeah. Got it.
So basically what you are doing is you are searching for that function, okay, t of x, which would give you the maximum value for that optimization problem at all t's, sorry, at all x. Okay.
Yes, sir.
Now, if you get that function, then this inequality will become equality. If you get that function. Okay. Now, what is the script T? Script T, you can visualize the script T as a bucket of large classes of functions. So you are choosing from a bucket of family of functions. Okay. Now, if you in that bucket of functions that you are searching over, if you can get a function small, I mean t of x, such that it is equal to t star of x for all x, then this becomes equality.
Yeah.
Okay.
Okay, sir. Yeah.
But if you cannot get that function, if you get another function t of x, which is not equal to t star of x at even at 1x, then it becomes inequality because at that x, your t of x is less than t star of x. Got it, no?
Yes, sir. Got it.
I can
Thank you.
write it maybe. Uh, I will write that here. Inequality arises because t of x, right, is less than or equal to t star of x for every x. That's all. Okay. If t of x is equal to t of x star, oh sorry, t star of x star at all x, okay, then equality. Yeah, I think that's worth writing. And see, one other thing, I'm almost ensuring that whatever I say, whatever storyline that I build, I'm writing all of it, right? One after the other, right? I mean, I write this as goal, questions, and all that. So this notes, right? Please go through it before you come to the next class. Every class, go through this line by line, step by step. Also, you have the recordings, watch the video, and come to the next class. That will help you a lot. And of course, we are available for questions over WhatsApp and Teams. Okay, Raghavendra Nayak.
Yes, sir. In this case, this t of x, do we choose any function and then try to optimize it, or we try
Good,
to?
good question. See, if you know how GANs work, other than this network, there is another network, no, which is called the discriminator network.
Yes.
That is your T of X. The need for another network comes up because you have to choose from a bucket of functions and you optimize when you pick those bucket of functions, you approximate those functions using another neural network. We will see that now.
Okay. Okay. Yeah. Thank you, sir.
Okay. Any other question? Okay. Great. Yeah, Harish.
So, So this T of X is also a convex function?
No. See, this T has nothing to do with that F. See, F divergence in the F function in F divergence, no, that our definition, only that is convex. Nothing else is convex. This F function is convex, that's all.
Got it.
Should we move on? Okay, let's get to. See, on a lighter note, the person who put this feedback, no, please don't take it badly. I mean, there's no. Anyway, it's anonymous, but it was pretty funny. So I received a feedback where somebody said that I'm paying this much fees to ISC for this particular course, so I expect this, right? So, I mean, one thing was it's very, very revealing for me that this course costs this much money. I didn't know that. Apparently, every credit here is what, 20,000 rupees, no? I was thinking that all this is reimbursed for you from your respective companies. Don't they? I think they would, no? I mean, there is some learning program that's always there. You don't pay this fees from your pocket, do you? Just curious.
Not
I mean,
true for all, not
I'm
true for
not asking,
everybody.
I'm not asking for, that person who wrote, okay? I don't want to know, I don't wish to know. But yeah, in general, I'm asking out of curiosity. So, not all of you, like, your companies don't pay that, huh?
Partially reimbursed.
Partially reimbursed, huh? I see.
For
No,
us, it is
it depends on the
completely
company, I
sponsored.
guess. It's full, I guess. It's fully reimbursed.
It is fully
For,
sponsored.
fully sponsored for us.
See, that makes me feel a little less guiltier, you see. Okay, so
That's not true for all, sir.
then I'm guilty.
No,
Okay,
you are
yeah.
not guilty.
What was
No,
the
I'm
demand
just
again, please?
some demand, right? I mean, like, okay, you have to teach more practical stuff. I didn't pay the fees to look at math or whatever, right? It doesn't matter. That's fair also. The demand was fair. I mean, I'm just joking, right? I mean, the way of putting it that okay, I mean, this is the amount of fees that I pay. I mean, it's sort of exorbitant. That's a lot. I didn't know that this course cost that much money. Okay, so but they said that okay, paying this much money not to look at math or whatever. But then I thought, okay, yeah, it's a lot of money. I hope. See, if it's your company that is paying, I don't mind. No, they paid for all kinds of stuff. That's not big money for your company. But if you're paying it from your pocket, then it is. I mean, it's all relative, but still, yeah. So one credit apparently costs 20,000 rupees, right? In this thing, okay, which is considerable.
But this is one of the prime courses in the program, so maybe he felt like that.
How do you know that it's a he? I don't know. It
I don't
might
know.
be
I
a
mean,
she also.
yes.
Yeah, anyway,
So some
and
people will
whoever,
say this is the
yeah,
course I'm doing the MTech for.
it's
Because
okay.
people
See,
like that, then yeah.
I mean, I understand, you to, I mean, don't get me wrong again, that the customers always have their right to question whatever the product that is being. See, everybody now talks of customer obsession and all that, right? So, customer is thinking that is the reason I put that feedback form out, and it is totally anonymous. And whoever wrote that, please don't get offended. I'm just taking it lightly. So whatever you think is a fair demand, put it out there, and I'll be happy to incorporate as long as I can incorporate. Okay. Yeah. Okay.
Sir, how about the offline classes? Student also register for this course and elective subjects, or it's a generic one, like 3-4 classes for them?
Come again. What is the question?
I mean, how offline classes goes? They need to register for this core courses, or it's scheduled for them, like first year these classes,
No,
next
no,
year this
no,
one.
no, no. Very similar to you. I mean, there are core courses, just like you have 3, 4 core courses, right? They would, I think, have some 6 core courses. Rest of all are all this thing electives. And by the way,
Okay.
I also teach this course, right, offline, and I'm doing it in ISC right now. That class also has 100 plus people in ISC, and trust me, that's at least 2, 3 times more mathematical than this. Okay, I know that most of you people are, well, not most, all of you are professionals and might have been a little out of touch from maths. There I do like much more maths than this. So this is not the upper bound of maths that one can do in this course. So please be rest assured on that. But anyway, so if you have anything that you would like to see as a change in this course, let us know. That is why we have that feedback thing, and we are happy to listen. Okay.
Modes are in a regular product development, like this type of maths, we are rarely using, right? So
I mean, did I become judgmental? I mean, I'm not complaining at all. I completely agree with you that you don't use that. But that is why, I kind of, uh, yeah, so make it accessible. I try to make it as much accessible as possible. But see, there is another way to teach this, I'll tell you honestly. I can completely get rid of math and only teach it like what is done in Coursera, right? Or this Android kind of stuff where I just give you algorithms and tell you, put some block diagrams and tell you how to do it. But honestly, right, as an instructor, I don't see value in doing that. See, whoever has done this course before, again, this is not self-bragging, have told that doing it this way, while difficult, while it is difficult during the course time, right? But if you put in enough effort to understand and do assignments and tutorials and all that, they have been benefited from this. This is what will actually differentiate you people from everybody and their grandmother who does machine learning. So everybody is a data scientist these days, right? What differentiates, I mean, somebody who knows well and somebody who does not is that some of the fundamentals and you can go more deeper into it. So there is value in doing math. It's not that it's totally valueless, but I understand that it takes a little bit of more effort. But yeah, that is what I expect from you people to do. Having said that, you can let me know if all of you think that the math is completely valueless. It's much easier for me to teach the algorithms and Coursera way. We can do it, but again, that's not my recommendation though. Okay, so let's continue. So what we had was that we had this carved lower bound on DF divergence. Okay, let's start from date given. So we are given data. Data set. This is drawn ID from PX. Sorry, drawn from PX. Okay. Now we have constructed an F divergence between, okay, before that we'll write what our P theta is. So we have this setup where there is a neural network. And the way I represent neural networks, right, they represent the dimensionality of the data. So this is a neural network whose dimensionality keep increasing as you go deeper and deeper. By the way, did Chandan do backpropagation for CNNs or was it only for MLPs?
MLPs, but for
Only
CNN.
MLPs? Okay. Okay, then you should look at backprop for CNNs, okay? Just as an exercise. When it's not completely needed, but it's a good exercise to do. Okay, G theta and whatever we get at the output is what we call as X theta. And this has distribution P theta, right? This Z was coming from normal distribution. Now with this setup, we constructed a lower bound on the distributional divergence between Px and P theta. Okay. This we said was greater than equal to this maximization over a class of functions. So what does this mean? This actually means that you are searching over a class of functions script T, and the thing that you have is you have an expectation here with respect to t of x as x comes from px. You have another expectation here with respect to f star of t of x as x cap here, as x cap comes from p theta. Okay, this is what we have seen so far. Now the question is, so recall that we are interested in, recall. So we're interested in finding out a theta star, okay, that is the minimizer of the f divergence, right? This is what we wanted. We could not do it because we didn't have access to px and p theta. So we approximated that by the minimizer. And this minimization is over theta. Okay. Minimize this, minimize the lower bound. Okay. Now, which is, and by the way, all of you understand this notation argmin, right? Have I explained the notation argmin? Done it, right? I mean, it is that set of theta which would minimize whatever is there within the function. Okay. Min is the minimum value. Argmin is the minimizer. Okay. The argument which minimizes. Fine. So you have to minimize over theta, which is the lower bound. Note that the lower bound itself has a maximization over t. Differences of this expectation, I will not write it. Expectation over px minus you have expectation of something with respect to p theta. This is what it is, right? Okay. Now this will become okay. Maybe before that, let us do this. Okay. Now this minimization, right? The outer minimization is min with respect to, is pay attention here. This is min with respect to parameters of a neural network, correct? Theta are parameters of a neural network, and you need to minimize a function or a value with respect to parameters of a neural network. Do we know how to do that?
Backpropagation.
That is backpropagation. So you can do this using backprop. Backprop over what? Over the G theta network. Okay, that's what it is. Now this is maximization with respect to class of functions. Do we know how to solve that? We don't. So we don't know how to optimize. We know how to optimize over parameters of a neural network. We don't know how to optimize with respect to a class of functions. So what do you mean by optimization over parameters is that, I mean, we can do a gradient descent in the parameter space, the space of parameters of a neural network. But we can't do gradient descent in the space of a function, right? We don't know how to search over functions. We know how to search over parameters. How do we get rid of this problem? Is that so you translate this into, okay, do that, represent script T, which are the family of functions that we are optimizing over via neural networks. Let's call them TW of X, where W are the set of parameters, the set of weights. I use the word weights and parameters interchangeably. Weights or parameters of a neural network. Now with different W values, okay, you will get different functions Tx. Do you agree? Because it is represented using a neural network. Yeah.
Sir, can I ask a question at this moment?
Okay, go on.
Sir, we are trying to represent the set functions using neural networks. I'm just trying to understand, let's say we want to represent a cubic polynomial or a polynomial of nth order. Then in that case, how will we represent it using neural networks?
Easy, right? So now this function, cubic polynomial, right? I mean, are you talking about a polynomial, a vector valued polynomial or a scalar valued polynomial? If it's
Like anything, sir.
Yeah, if it's a scalar valued polynomial, then what do you need? So let's say that f of x is equal to ax cubed plus bx squared plus cx plus d, right? Right?
Yes.
So you build a neural network that will take x as input and give you f of x as output. See, that's what you do in all classification and everything, right?
No, sir, like there, like if we consider a multi-layer perceptron, so we have the weights, we have the bias, okay? And then eventually for each layer, we have a non-linear activation.
Correct.
Okay. So I'm trying to understand there, like how, let's say I want to do x cube. Okay. So that case, how will I do that?
You can, right? See, that is the regression problem. What you are saying is the classical regression problem. Okay, so let's say that your f of x is equal to okay. So what you have is for different values of x, you have f of x. So what you have is let's say it's x1 comma f of x1, x2 comma f of x2, and so on. You have xn comma f of xn. This is your data, right? This is what you have. You should have this to represent this as a neural network.
Yes, sir.
So what I do is I will have an MLP which will take x as input. So it will take xi as input and it will predict f of xi as output. This is the predictor. Now, how do I train this neural network? This, let's call this f cap x of theta. That's all. Theta star is equal to minimum of, we have n samples here, 1 by n, 1 through n. I'll take f of f theta of f cap xi minus f of xi. That's all, no? This is classical neural network training. This is solving a regression problem.
Got it, sir.
This is how we are representing this polynomial function using a neural network. See,
So
that's
just a
what
comment. So the presence of nonlinearity allows us to also model this nonlinear functions, right?
Well, yeah. See, okay, that is some other neural networks. The deep neural networks are universal function approximators. That is why they are powerful. Okay. Now, what does this mean? That means that by choosing the weights and the biases and the nonlinearity of an MLP, which is deep enough, you can represent any function to arbitrary closeness. That is a known result. That is why the go-to architecture for all machine learning these days are neural networks. Is that fine? Okay, so I think we'll remove this.
So one question here.
Yeah.
But here we like already know that function should be like tx, right? Like t of x. So can you put some restriction on that so that it will
No,
can
with
give the
no
result faster?
where is
Not in,
what do we
not
know? We
here.
don't know. I understand. We don't know anything about T. What do we know about T? We know nothing about T. See, in the divergence case, T is simply a class of functions. See, what we know is that this T has to be such that it is a solution for this inner optimization problem for all x. But we don't know anything beyond that, no? See, we want that T to be such that it maximizes whatever is there in the internal bracket. That's all. See, just like we had that regression problem that I had written. So here you are only solving an optimization problem with respect to this T. So T is a neural network. Okay. So I'll write that
we
down.
know here it should be the maximum value, right? So at least that conditional things can be
No, how? See,
feed
we
into
want,
the.
see, this is an optimization problem that we are solving. Just, okay, I erased it. It is no different from the problem that I had just written. So you had to minimize, you had to find a theta such that it minimizes the differences between norm of these two functions, right? That is what we had for the regression problem, isn't it?
Yeah.
This is exactly the same. Instead of having the differences between the predictions, it has some other expectation. That's all. You are trying to maximize. See, maximization, minimization are both. I can write this minimization as maximization with a minus here, correct?
Correct.
Same thing. That is, we don't know anything. We only know that this neural network has to maximize whatever is there inside. Okay. Now I will write that. So now, I mean, I hope that all of you understood what I mean when I say that I will represent this T function via a neural network. Okay. Now what happens is we will write down. So with this, so now we have a G theta of Z network. Okay, that would take the Z and give you X cap from P theta. Okay, so maybe we okay. For completeness, we can write. We have another network now, neural network. Which is TW of X. It will take X and it will give you the output TW of X. Understand? Now there is a particular loss function which is, okay, let us write that as loss. It's like not loss, right? It as cost functions is equal to the expectation of T of X as X is coming from P theta minus the expectation of F star of T of X cap is coming from F X cap, sorry, coming from E theta. Now, what happens is we need to find the optimal W for this T network such that it maximizes this cost. Do you agree? Does all of you agree? Let me just see what is happening here. Look at this, right? We have to find the T network or the T function such that this cost is maximized, correct? All of you with me on this?
Yes, sir.
Okay. Now we want to find theta, okay, such that it would minimize the same cost. Okay, I'm sorry, I should write it as argmin and argmax, right? Because W star is not the minimum value of the function, it is the minimizer of the function. So it is the argmax with respect to all possible W's, and theta has to minimize the exact same cost.
Sir, is the first one is P of Px, right, instead of P theta, the cost formula?
Correct. Thanks. This okay? So there is a cost function, okay? And there are two neural networks here. So one neural network has to maximize that cost, and the other neural network has to minimize that same cost. Now, where is this coming from? You look at this, right? Let me write that down. So now basically what is happening is, so we have represented the T function. So first what happens is that you construct a lower bound on your F divergence by maximizing this expectation over Px minus expectation over P theta. So you maximize this with respect to W, you get a lower bound on what? On F divergence. Correct? We completely write it so that it is it's an expectation over T of X. Okay, TW of X now, right? Because it is parameterized using another neural network now, minus is another expectation with respect to P theta of F star of T of X cap, TW of X cap. Now you optimize this with respect to W, you get a T function, which is actually a neural network. Now that would create a lower bound on this thing, right? Solving this creates a lower bound on DF. Correct? You recall what was happening, right? So this lower bound is created by maximizing this. Now, if you choose one T, it will create one lower bound. Do you agree? One particular T function will create one particular lower bound. Correct? You also note that the lower bound that we have constructed, right, on DF for a particular theta. What does that mean? See, look at that. This loss function that we are calculating, no, is a function of theta. Why? X cap is a function of theta here. Do you see that? The X cap that we get, right, depends on theta. So it's a function of theta. The loss function is a function of theta. Do you agree? So for a particular theta, okay, maximizing this thing will create one particular lower bound on DF. Correct? Now, once you create a lower bound on the F divergence for a particular theta, you want to minimize that lower bound, okay, with respect to theta. Okay, I don't have space to write it here. Write it here. Now, this minimization, okay, minimizes the lower bound, minimizes that lower bound okay, created by TW in the previous step. Do you understand what is happening? So first you have a T function, okay, that would create a lower bound at a particular theta. So you start with some random initialization for this d theta, okay, so, and then you train this TW network, okay, you create a lower bound. Now with that lower bound, you have to minimize that lower bound, right? Because ultimately the goal is to find a theta that makes P theta close to Px. Now we are not minimizing the exact F divergence, we are minimizing the lower bound. Once you create a lower bound with a particular TW, we note that after you train this network once, okay, one T function is fixed, created actually. So once you create a particular T function, then there is one lower bound that you have created. Okay, and once you create a lower bound, you train this neural network to find a theta that would minimize that particular lower bound. Okay. Now, once you have minimized that lower bound, you can again come back to this t function and change the t function again, which would create a new lower bound for that new theta that you have learned. Do you see what I'm saying? See, the lower bound is created for a particular theta. Do you understand? Now, given a theta, t will create one particular lower bound. Now, once a lower bound is created, you can tweak your theta in such a way that your p theta gets close to a px. Okay. Now, with that p theta, changing your t function again will create another lower bound. Maybe it's tighter this time. Okay. Then with that lower bound, you go back to theta and you keep alternating between these two optimizations. Do you see the picture? What is happening? Now in a GAN, right, you know that there are two networks, right? And by the way, this network is what is famously referred to as the generator network. Okay. And this network is referred to as the discriminator or the critique network. See, in the next part of the class, I will give you concrete examples for one F divergence, which is the original GAN formulation, and actually show the loss equations and backpropagate and all that. Okay. But here I want you to understand the abstract picture that there are basically two functions. Why do you have this discriminator network? This discriminator network is simply creating the lower bound on the F divergence. And lower bound itself has a optimization problem that is to be solved, right? Once you solve this inner optimization problem with respect to W, okay, you get a lower bound and for a particular theta, and you minimize that lower bound with respect to theta. Okay, so you have gotten a theta that has minimized the lower bound. Now, what is the guarantee that the lower bound that you have constructed is tight or good lower bound? So, with a theta that is closer to the uh, PM, you create another tighter lower bound and you keep alternating between these two. See, these kinds of problems, I will take questions in a while. So suppose you have a loss, okay, a cost, okay. So it depends on, let's say that this cost depends on two set of parameters, theta and W, okay. Now what you are doing is you are maximizing the same cost function with respect to W and you are minimizing the same cost function with respect to theta. So basically you are seeking the theta star and W star, which would simultaneously maximize this loss function and minimize this loss function, right? So what is actually happening is that imagine that you have I mean, I can't write it in two dimensions. That is the problem. So basically, imagine this cost. Okay, let's say that both your theta and W. Okay, theta is one axis here. Okay, and W is another axis, and your cost function is something like this. Okay. Very difficult to write that sadly. Anyway, so if it's like this, now what am I seeking is I am seeking a point, right, in the theta comma W axis, okay, in such a way that if I move in either of the directions at that theta star, the function increases. Okay, if I move in the either directions of W, okay, at that W star, the function decreases. Do you see what is happening? So there is one function, okay, one cost function, which is a function of two set of parameters, theta and W. Now I am seeking a point theta star and W star in the parameter space such that if I move on the function around that theta star, the function value increases at both the directions. And if I move along the w direction at that particular point, the function value decreases. Do you see that? Okay, so these kinds of points, right? These kinds of points are called saddle points. Because they're like horses saddle, right? I mean, you know what saddle is. Saddle, if you move along one direction, at that the function increases. If you move along the other direction, the function decreases, right? That's why it's called saddle points. Now, this sort of an optimization problem, right, where you are seeking saddle point of a function, they are called adversarial optimization. That's why the name adversarial, adversarial networks. Or adversarial problems. So because of obvious reasons, right? So this inner optimization problem, right? Okay, is trying to maximize whatever you are trying to rather the outer optimization problem is trying to minimize the same cost function that you are trying to maximize using the inner optimization problem. So in that sense, the inner optimization problem is quote unquote adversary to the outer optimization problem and vice versa. See, in mathematical sense, you are simply seeking a saddle point. So GAN, I mean, the optimal value for the GAN, right? The optimal parameters for the GAN, the optimization problem that you are solving in a GAN is simply a saddle point problem, which is that you have the same cost function. We know why now, right? We have the same cost function, and we have to maximize that cost function with respect to one set of parameters W, and we have to minimize the same cost function with another set of parameters theta. Right? But where did this come from? It came from the fact that we started, see this network, the another T network came because, you remember the entire story, please. So you have a divergence metric between P theta and Ph, which you would want to minimize. Okay, you could not minimize that. So we constructed a lower bound. The lower bound that we constructed becomes is dependent on another class of functions T of x, and we represented those class of functions using another neural network, and that is why another neural network came into picture. Okay, see, as you can imagine, I'll explain. I mean, don't worry, I will tie all the loose ends in this class. But yeah, see, I mean, just as a side note, you can imagine that once we solve this optimization problem, this discriminator network is of no use. We'll discard it, right? Because our ultimate goal is to give a Z as an input and get an X cap that behaves like PX, right? So this is of no use. This TW network is only to construct the lower bound on the F divergence. So that is why it is used during training, but during inference or prediction or generation, TW network is not at all used. We will come to that in a while. But anyway, so we represented this T function using another class, another set of neural networks. So every time you get fix a TW function, you will get a lower bound on the F divergence. But to find this TW network, there is a maximization problem that you will need to solve. Okay, so this maximization problem that you are solving creates a lower bound on F divergence for a particular theta. Once you create that, you minimize that with respect to theta, which will minimize that lower bound which is created by TW in the previous step. And you keep alternating between these two. So create a lower bound, minimize it. Make that lower bound tighter, again come back and minimize it. Create another lower bound, try to minimize it, and you keep alternating between these two. So till a point of where do you stop this? You stop at a point where, I mean, how do you stop GAN optimization is a question that is that's not well answered. I will answer that in the next half of the class. But yeah, so this is how you do an optimization. I mean, that is why it's called adversarial problem, because you have the same cost function that is being maximized with respect to one set of parameters, and you are minimizing the same with respect to another set of parameters. Okay, so I will stop here and take some questions, and then we will break for a short break, and then we will come back and I'll make it much more implementation friendly, and I'll take an example for the divergence, and we will go to that basic GAN paper, right, which happens to be a special case of this. Okay, questions here. I'm sure there will be many. Please raise your hands if you have questions. lot of people raised your hands when I was explaining. Did I explain it in such a way that your questions are all answered? It's good to know. Okay. Yeah, Raghavendra.
Yes, so what would be the dimension of this TW of X? You've shown it as a narrowing, right? So
Yeah. That's a good question. Depends on the f function that you have chosen. For the naive, when your f function happens to be such that it is the underlying divergence is Jensen channel divergence, no, that happens to be a scalar, which could be interpreted as a classifier. I will show that in the next half of the class. That depends on f function, no, because if you recall the definition of our t function from the previous class, what was t function? T function takes x and gives out values from the domain of f star.
yes.
So whatever f star you choose, f function that you choose, this t depends on the choice of f divergence that you have made.
Okay.
See, that is why, okay, now that you asked that question, very relevant. See, if you choose your f to be Jensen channel divergence, this discriminator network will take x and give you values between 0 and 1. Okay. Now, if you choose your f divergence to be what is called as chi-square distance, I mean, choose your f in such a way, then your TW network will become a regressor, which means that the output of your TW network will be a real number. And that is why different f functions will give you different instantiations of GAN. So there is this LS GAN, least square GAN, which is just using an f function which corresponds to the chi-square distance. The naive GAN is when you choose your f function such that your f divergence is Jensen channel divergence. So if you choose it to be total variation distance, then it becomes TV GAN. So see what I have done. I mean, for you, if you people can appreciate, see when you write a class in object-oriented setting, you write the constructor of a class. No, that is what I have done now. Okay, so all these GANs are simply instantiations of this class. Right? If you can see the analogy. So what we have done is just constructed the family of GANs. So each of the thing would be an instantiation of it. Okay. Yeah.
Thank you.
Indrajit?
Yes, the difference or the cost we are maximizing is the difference between random, okay, x and x hat, right?
Difference between two expectations.
No, but x hat is the
output
data
of the x hat is the output of the G theta network. X is the data.
Yes, so we are taking the difference between these two, the
We are
data
taking
generated by us.
no,
And
hold be precise. We are not taking difference between the data points. We are taking the difference between expectations of t functions and f star of t functions, where this x star and x comes from the corresponding distributions. That is what it is. We are not taking x minus x cap here. We are taking the difference between the expectations of Tx and f star of Tx cap, as x and x cap are coming from Px and P theta.
okay.
Do you see that? The cost function is difference in expectations, not difference in data points.
Yeah, that's correct. So that's the difference between averages, right?
Difference between averages of not x and x cap again. Difference between the averages of Tx as x is coming from Px and f star of Tx as x cap is coming from P theta. It is again not the average of x, it is average of Tx. It is not average of x cap, it is the average of f star of T of x cap.
Okay.
Is that okay?
Yeah, and then this cost or the maximization should not be equal to minimization, which we are doing over theta.
What do you mean by that? I didn't follow the question.
First, we are maximizing this difference, right? And then we are minimizing the same.
So you should realize that maximization is with respect to different set of parameters, and minimization is with respect to another set of parameters. The cost function is the same, but maximization is with respect to W, minimization is with respect to theta.
So when we maximize with respect to W, are we not changing theta in any way?
No.
Okay.
That is why I said, no, it's for a fixed theta. So you alternate between those two. So I will also show the the way the gradients flow in both of these in the next half of the class. That is what I'll do. I will put out a particular f function and I will write down the gradients and also write the gradient descent equations which you would have to implement in your assignments. Okay. By the way, you will all be implementing all this. That is what you will do in your assignment, so that there is absolutely no gap between the maths that we have done and the implementation that you do. Okay. 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 Astic.
Yeah, so you mentioned that we are maximizing and minimizing the same cost function.
Yeah.
So it
But
is
but
happening.
hold on. But with respect to two different set of parameters.
Yeah. So it is sequentially or at the same time? It should be sequentially, right?
It is sequential, alternative.
Okay. And first we are maximizing, then for that fixed value, then we are again minimizing it for theta.
The order does not matter because you start from something and then you alternate between them. No?
Okay, yeah, that
Practically,
makes sense. Yeah.
order does not matter.
Yeah. Thank you.
Sachin?
Sir, can you what is the relationship between this? W is also a set of weights and parameters, right?
Theta
So in
is also a
tutorial,
set of weights, correct.
and theta was also, right, the parameters of that neural network.
There are two neural networks. One neural network I have called as W. The other parameters I have represented as theta.
Okay. So this W R max is that this discriminator or critic.
Correct. Both of them are back propagations only.
Okay.
Both the maximization, of course, no. Both the optimizations are solved using back propagation only.
Okay. And once we figure out, like, for one given W that you maximize the cost and then for theta you minimize. So like, do we compare for all different W's?
There's no different W. No, you are doing just gradient descent. See, one iteration through TW and you get a W, you get a lower bound. Now you get another, you do one iteration through G network, you get theta, right? Then you come back with that fixed theta, the cost function changes. No, see, once you change theta, the cost function changes.
Okay.
Now you come back to your W network, tweak your W again. And now the cost function has again changed. Go back to your theta network, change your theta and keep alternating between those two.
Okay, got it.
See, mathematically what is happening is that the moment you have a particular T that is fixed, no, there is a lower bound that gets fixed. But that lower bound need not be tight. Okay. The lower bound need not be tight. Okay, so maybe if you want, I thought I would do it at the end. Okay, let me save that for the end. Okay, because there is one picture that I write. You please mute. Huh? Okay. See, there is one picture that I write. Okay, of what is happening alternatively. That would give you. I mean, that would actually tell you a lot of story. But that I can write only when your T function happens to be a classifier. In the case where your F is Jetson-Shannon divergence. I will do that. I will do that in this class at the end of the class. You'll get much more clarity as we move on. Okay. Okay. Any other questions?
Yeah, sorry.
Yeah. Sushil?
We're maximize.
Yeah, sir, I have a question. In the cost function, I see you are representing one neural network in the form of TW. What about the G theta? Like, where is it reflected in the cost function?
X cap, no? X cap is coming from G theta. X cap.
Okay.
X cap is coming from G theta, no?
Okay, sir. Okay.
Yeah. Okay. Another question. Okay. Yeah.
When do we stop? Because we
Yeah,
are
I told you, right? I told you I will tell you the stopping criteria in the next half of the class. Okay. Yeah. So okay, we'll take a break. I think I've been here since 9. So we'll take a 15 minutes break. It is 11:10 in my clock. Shall we come back at 11? 20, 11:25.
30.
11:30. If we come back at 11:30, we'll only have 45 minutes. Okay, 11:30 is also fine. Okay, 11:30 we'll come back. As there's another, yeah, people can leave, but another interesting. So there is Abhitosh, are you there? Okay, I think he's not there. Yeah, this his name and my name mean the same, by the way. Okay, like in in Sanskrit, right? The word tosh represents happiness, and any prefix that you add to it is just qualifying that. So some is a prefix that would qualify that. It says, exalted happiness. So santosh is, of course, you know what that means, right? So pra is another suffix in Sanskrit that would have the same meaning. Now, that's my name. And Abhitosh is one other thing. So yeah, that's. I was looking at his name and I just got this thought and thought I'd share you, but share with you the person is not around. Anyway, doesn't matter.
Abhi
Okay.
and para are opposite or same?
No, same thing. Abhi, pra, sam, all these convey like magnification of whatever you are saying. Right. So tosh is happiness. So santosh, abhitosh, pratosh, all these they mean the same. So you might have also heard this name of Ashutosh, no?
Yeah.
Right. Ashu means quick. So that's why the Shiva is called Ashutosh. Somebody who gets happy very quickly. So that is just a little different. But Abhitosh, Santosh, Pratosh, all these mean the Paritosh. Yeah, I'm not Paritosh, by the way. My name is Pratosh. Okay.
Yeah.
So, yeah.
Seems like too many happy people in the team. Abhishek.
I always tell my parents that it's a misnomer. My name is. Right. So I don't know how happy I am in my life, but yeah, they named me happiness. Yeah. And what's more interesting is when my parents named me, they didn't know what my name means. Somebody suggested, and it looked unique, and they just chose that name. So then, I don't know if how many of you know that. I also happen to be like interested in Sanskrit and Indian history, philosophy, etc. Studied Sanskrit for a long time. Then I realized what the meaning of my name is. Yeah. Anyway, this.
Sir, on a
Because
different note, I think
Hey,
we are.
hold on.
Hello?
See, we are in the break. People can leave. This is all not in unrelated stuff. But yeah, so go on. Whoever wants to say.
Yeah, sir, actually, I think you membered in the Sanskrit club as well, right? So I thought there will be some way of teaching from the scratch. That was my interest point to join that. So is there any such
See,
things are going on?
I'm not an active member there. I mean, it is
Okay.
mostly like headed by Sangeet and Shankar Rama and these people.
Okay.
So I don't have a lot of say. See, when I was in IIT Delhi, I used to teach Sanskrit to people like undergrads there. That was my. Here I have too much. Then I didn't have a family. I have two children, and
Sir,
I
sir, sir, what is the thing like you resigned from IIT Delhi and came to IISc?
yeah.
I mean, why you resigned from IIT Delhi?
Because Bangalore is my home. I'm a South Indian guy and उतना गर्मी और ठंड को मैं सह नहीं पाया.
Oh,
Anyway, that's actually, yeah, I mean, come on, right? I mean, say here, anything more than 30 is hot for us and anything less than 20 is cold for us. And मुझे अब दिल्ली में रुक दो at winters को 0 डिग्री तक जाएगा, समर पे 50 का ऊपर जाएगा, right? It was too much.
yeah, correct.
That's the only reason. Otherwise, I was very happy at Delhi. Professionally, there was absolutely no problem. And see, when I went to Delhi, I thought that I would want to come back as soon as possible. In fact, uh, because you asked, when I was applying for faculty positions, I applied to Bombay, Madras, Delhi. Okay. I could not apply to ISC because I did my PhD from ISC only. No, they will not take their own students unless they go out for some years and come back. Now that option was not there. I applied to Bombay, Madras, Delhi, and my preference was, of course, first preference was Madras, and then it's Bombay. Then you move up the map, right? But the first offer was made from IIT Delhi. So,
Sir, you PhD, you done PhD, right, sir?
because otherwise you can't become faculty in any of these places.
Sir, from where you did this PhD? Which
Told you,
college?
no? IAC only.
Oh, IS itself.
Yeah. Yeah. So, like 10 years back, 15 years back, I was a student at IAC. So, इसलिए forcefully I went to Delhi, but what I was saying is, when I went to Delhi, I started liking it. I mean, some of my colleagues at Delhi told me that Delhi will grow on you, you will start missing Delhi and all that. I never thought I would miss Delhi, but abhi I miss Delhi because there are lots of good things about Delhi which is not there in Bangalore. Bangalore is it's a doomed place. I mean, infrastructure is so bad. I mean, even though I come from, technically, I'm not from Bangalore. I'm from a place called Mysore, which is 150 kilometers away from my Bangalore, which is heaven. Yeah. But this
Mysore
Bangalore
Palace.
is, yeah, like Bangalore is hell. I mean, all broken infrastructure, rude people, right? You know what? I felt people in Delhi more softer compared to people in Bangalore. Everybody says that North Indians are harsh and nothing, but I mean, आपको हिंदी में बात करना पड़ेगा. That's all. The moment you start speaking in Hindi, and people are people are more cosmopolitan and more softer there. यहाँ पे तो my God. I mean, it's dreadful when I see auto drivers and all the other people here. Okay, this is getting recorded. Don't put it on some social media, right? I mean, IAC professors make some comments on. So these days you cannot have a casual conversation with people, right? They will record and put it on social media. It will become a national news. See,
These things should not go on live, sir. Definitely.
I'll tell you. I mean, I just some 2-3 months back I gave a talk somewhere. Okay, something on philosophy. Somebody called me and I gave a talk. I mean, when I was giving a talk, I never knew that okay, they were recording this and all that. These people have recorded and put it on YouTube. I mean, this thing has become a big thing, right? The people are tweeting it right, left, and center. There are views for it, against it, and all that. Then I had to contact these organizers of that talk and ask them to put a disclaimer saying that the expressions, all the expressions or opinions are of the author and has nothing to do with ISC. These people who have put it online, no, they have used my affiliation. They have called it, oh, ISC professor says this. I mean, which is true because I am a professor from ISC, but those are my views, not my university's views. No? Some of them may be politically correct, some of them are not politically correct, and yeah, that might cost my job also. So it should be very, very careful when you talk,
Sir,
especially
one more
I
these
think,
days.
sir, I think, sir, when you start the class, you should put the same disclaimer.
No. This is okay. No, this is all technical content. See, this is all like, this is all standard stuff. You can quote me saying, oh, IAC professor said that GAN solves a paddle point problem. No problem, right? I have no problem with it. Oh, IAC professor said that you train a neural network using back propagation. Nobody cares, which is true. Now, if I start making statements like, okay, statements regarding some history, philosophy, language, some sensitive issues, if you quote me on that and if you tag ISC's name there, it's not correct, no? It's all my opinion, and I am entitled to having my opinion. But I should not be, as a government employee, I should not be having opinions that are. I should rather not make my opinions public. See, you saw what happened, no? Recently, Prime Minister went to CGI's home for a festival and it became a big national news, right?
So there is
Sir,
a video of you, sir, where you're explaining Aham Brahmasmi from Sacred Games.
Arey yaar, that's what I'm saying.
sir, on the same lines, I saw your video on the
No,
Vedas,
that's a see,
and
that's a rabbit hole. Please don't start that. Okay, so let me stop.
sir, I want to like ask you like how